Our next speaker is a local. It's Richard Nickl from the Statistical Laboratory here at Cambridge, and he's talking about statistical guarantees for Bayesian UQ in inverse problems. So, thank you.
Okay. Thank you very much for the invitation. So I'm slightly new to this crowd, although we sort of study very similar problems, sometimes from a quite different perspective, and I'll try to maybe build some bridges here in this talk. So, we're statisticians, and we start with some statistical model. We have some distribution y. I realize that the notation will maybe not always be uniformly aligned with, for instance, the previous talk where y was the parameter. But anyway, as you have some model that you specify by writing down the likelihood, and then, you don't necessarily have to be, but you might want to be Bayesian, and you sort of start this game of specifying these conditional distributions coming from your model, and then you sort of just update and you find the distribution of the parameter given the data. And I guess this workshop is probably mostly about how to computing these posterior distributions and aspects of it. I'm actually not really talking about that at all. I'm trying to give some reasons for why you should be computing this distribution and whether it has any perhaps sort of prior independent properties that we could even call maybe statistical optimality. And the thing that we really care about, since it is uncertainty quantification, is sort of these error bars that people like to report. So you might call them maybe a credible set. So you might take your posterior mean or mode or something like that, and then you would look at sort of somehow the spread that your distribution generates around that algorithm that has generated theta bar, which is sort of your point estimate. And you don't use any sort of frequentist quantiles. You just use the posterior quantiles to plot these credible sets. And the question is, are these credible sets any good? Should I compute them? Because most of the times, in particular in high-dimensional situations, the prior serves as a regularization tool and not as something that comes from subjective knowledge. And I don't even want to enter this philosophical debate. We will all agree that if I can actually prove that this is a good algorithm completely independently of the prior, probably everyone will be happy. Or no one will at least say that it's not a good result. Okay, so in terms of pictures, you have your MAP, you don't know what a true function is, and you sample 2,000 posterior draws, you get something like that. And the question is, if you use this decision rule maybe to reject hypotheses on 10,000 different data sets, are you approximately maybe a large proportion of the times going to make the right decision if you postulate that there is some true function underlying the data generating process? Okay, so it's a question you can ask. I'm not the first to have asked that. Actually, it goes back pretty much more than 200 years to Laplace in his treatise on probability theory, who sort of proved the first kind of theorem in that direction, where he sort of realized that in simple parametric multinomial models, this posterior distribution, if you take a fairly harmless prior, as sample size increases, starts to look an awful lot like a normal distribution. And of course, he didn't see this in simulations, he just proved it. Yeah? And he proved this under the assumption not that the prior actually represented anything informative about nature. What he said is actually the y we condition on the data follows a fixed distribution, theta naught, that is sort of the ground truth of my model. And it doesn't just converge to some normal distribution. It actually converges to a normal distribution that is centered at something that the frequentists that you might think are from the other camp, but what this theorem really tells you, there are no two camps, there's just one, might use, which is the maximum likelihood estimate. And also this curvature of this normal distribution looks pretty good in the sense that it picks up the inverse Fisher information. So in some sense, the spread of the posterior distribution asymptotically aligns with the minimal spread that any procedure could ever have in making inference on theta. And sort of this was worked out in more generality by Sergei Bernstein, who was one of the leading Russian probabilists of around 1900s. Von Mises, who was an Austro-German mathematician who then left and was in Harvard for many decades after the war. And LeCam, probably, who was sort of an eminent mathematical statistician in Berkeley, put this into its final form. And you can also replace the maximum likelihood estimator by the posterior mean, saying that the posterior distribution sort of in this frequentist large sample size or small noise scenario, if you center it at the posterior mean, which often could also be the MAP estimate, will produce the same approximation. And this approximation holds in a very strong sense. You have two random probability measures here. Here's the posterior, here's the normal distribution centered at a random point, random under the data now. And if you take, for instance, the total variation distance between these two, this will converge to zero almost surely under the law of the true data generating process P theta naught. The only I'm just out of curiosity in this crowd, who has heard about this theorem before? Maybe you can raise a hand. Okay, good. Yeah. So then the question is somehow, in the statistical data science age we live in today, what remains of that theorem when you go to high-dimensional parameter spaces? Okay, and then particularly we think that sample size might be large, but the number of unknown parameters might also be large. Can we still say something like that? But before I'm going to talk about it, just why would I want to prove this? Well, if you have a theorem like that, it actually tells you not only that the posterior is approximately normal, but it tells you that these credible sets, sort of the way you form decisions in Bayesian statistics, are actually perfectly aligned with the frequentist interpretation of a confidence set. So if you have that theorem, you can show that the credible set most of the time, sort of you change your tune your significance level at 95%, then actually if you use this decision rule on repeated data sets, then approximately 95% of the time the credible set will actually contain the truth. So this sort of giving a frequentist guarantee for the algorithm, and it's not because the posterior just puts, basically the credible set everywhere. It has a diameter that has sort of the right size in this parametric model, which is 1 over square root of sample size. Yeah. So yeah.
Sorry, I'm still struggling with this, the statement of the theorem. So what are the preconditions? Because
sure. I mean,
it's not the case that you can have a likelihood function, which, for example, will always give you a bimodal likelihood, right? 2 peaks, right? And so your posterior will never look like a normal distribution.
Well, I mean, obviously, I'm putting this informal here. So you need several things. You need that the prior has a positive density on your parameter space. So if you take a normal or distribution of full support, this is fine. And then you need something that Lecam called a locally asymptotically normal model, which is a certain assumption on the asymptotic expansion of the log likelihood ratio process. So there are some assumptions on the parameterization of the model, which, however, encompass a large class of models. And certainly, if you have an additive Gaussian noise model, you will be in that class, no matter what the parameter space is. If you have, so you need some a little bit of assumptions. I can give you references for this. But if you have that theorem, it is sort of uniformly good news, and you will say that these credible sets, without having to go into this tiresome Bayesian versus frequentist debate, you can just say the Bayesian algorithm works, period, and we don't have to discuss it, okay? And so what happens when you go to infinite dimensions? Well, there was David Friedman, who was an eminent probabilist and statistician in Berkeley also, chose the Wald lecture, which is one of the main honors you can be given to give in the Institute of Mathematical Statistics, to give it on a subject which is to show that when you try to prove Bernstein-von Mises theorems in infinite dimensional parameter spaces, so when you do non-parametric regression, for instance, where you actually, if you think of the previous talk, you have a series expansion and you don't put a bound on your series expansion now, you let it go to infinity, so you have an infinite dimensional model, you might then still compute somehow the analog of the Bayesian, say, Euclidean credible ball. And what he showed in this lecture, which was published in Annals of Statistics in 1999, that there are simple situations where you have a Gaussian prior and a Gaussian error model, so everything is nice, but the confidence set does not work. In particular, the frequentist coverage probability can go to 0. So, you can maybe, when you publish negative results, you never get a lot of credit for that, but this is actually a good result that one has to be a bit careful when you use the Bayesian method for inference if you want to give frequentist justification of it in infinite dimensional models. Now, this is something that I and Ismael Castillo a few years ago revisited, and we showed that there's some sort of, mathematical obstruction in that theorem that has to do with the fact that these Bernstein-von Mises approximations, when you want to prove them in high-dimensional models, somehow it has to do with the choice of norm, which we all know in infinite dimensions the choice of norm is an important choice. And while in L2, indeed, this Bernstein-von Mises theorem doesn't hold true, you can find certain function spaces of negative smoothness, if you want, where you can get a Bernstein-von Mises theorem in a direct model. So I'm not talking about inverse problems yet, okay? And so in a way, it has to do with the choice of geometry. You could say that the Bernstein-von Mises theorem holds sort of weakly, but not strongly, if you think of sort of PDE solutions terminology, although it's a bit more subtle than that, yeah? And in this talk, I'll try to tell you a little bit about whether or not one can adapt sort of theorems of that kind to the inverse problem setting, particularly to nonlinear problems, and how the theorems read out in the end, and what you might conclude from them about the difficulty of using Bayesian inference in inverse problems. Okay, so let's put this, I'm actually mostly going to talk about 2 examples, but the theory I present is somehow a template for general settings, so let's put this into a general setting. You have some forward problem between Hilbert spaces, just like in the previous talk. You might say that you measure actually just the finite dimensional aspects of this solution of the of this forward map, In the easiest case, you could think of point evaluations, where you just have a domain where you sample the solution of your PDE. And then I will take sort of the most basic of all noise models that you actually observe all these real valued measurements with additive Gaussian noise, unit variance. You could of course debate about this, but at least this is something that Gauss first wrote down, so it is a sensible model to just assume that. And for the theory, in some sense, if you want to prove anything, it is quite convenient to assume that the discretization step has been done for you, which is typically something you can deal with. So we then pass this to the kind of continuous analog of this model, sometimes called Gaussian white noise model, where you actually see the PDE solution, the forward map, and then you have this additive Gaussian white noise at a certain noise level that scales with sample size. And so you can already see, if you know a bit about Gaussian white noise, that unless your ambient space in which your forward problem lives is finite dimensional, this noise term here is typically much rougher than the solution of the PDE. If you think you have a solution of a nice elliptic PDE, it should be an H2 function, but the additive white noise lives in a much bigger space. Yeah? So denoising nasty noise that is much rougher than your forward data is something that is not completely obvious how you would do this. You can't just use a simple perturbation analysis. You have to do some statistics. Okay, so of course, one thing that if you don't want to think about this too much about each forward problem, each inverse problem in itself, you can take a principled approach that Andrew sort of pioneered in this inverse problem setting, and just to say I'm kind of going to be Bayesian, I will put some prior on this function f that indexes sort of that is in the domain of my forward map, and I just play Bayes' rule, and in the Gaussian additive white noise model you can derive Bayes' theorem fairly quickly from some basic probability theory, Cameron-Martin theorem effectively. So you can write down this posterior distribution. And of course there's, you know, some ingenious methods are required to sample from it, but I'm not talking about this. I'm trying to understand the statistical behavior of this distribution. And okay, so particularly why do I think that this frequentist way of thinking about a fixed distribution having generated the data is quite convenient in this setting? Because the prior here does, in my opinion, not really represent a subjective belief. It is something that serves as a regularization tool. For linear problems, we even have a one-to-one transfer principle that tells you if you take Gaussian priors, then the MAP estimate is just a Tikhonov regularizer, so with a certain penalty. So in a way, the prior is a bit dual to the choice of the penalty function. So we should analyze these methods independently of the penalty choice, or independently of the prior. And moreover, of course, you get uncertainty quantification, which is sort of something that means that you can actually look at the posterior draws and they will give an idea of how well your algorithm has done, and you might want to investigate whether guarantees can be given for these credible sets to be confidence sets, also in this inverse problem setting. And I will look at two examples for which we can prove some theorems. It turns out that the theory for these problems, PDE type problems, depends on, you know, at least with mathematics, I know you have to make a case-by-case analysis for reasons that we will see in the theorem for a moment. So I look first at something that comes from X-ray transforms, or is somehow also related to transport PDEs. So you have a nice manifold in RD, think of the unit disk, and you somehow see solutions of a transport PDE, or if you want, you see the X-ray transform where you integrate a function along certain geodesics, and then you see this sort of for all geodesics, or some discretization of geodesic space. And this f somehow is the source function of your first order transport PDE, and you might want to be able to say something about this function f from these line integrals. So of course, if you just in the unit disk have flat geometry, it's just a radon transform. And this is a linear problem. The more interesting theory will come for the nonlinear problem in my second example, but as a teaser or as a sort of way to prepare the stage, this is already quite useful as an example. Okay? So the goal is now to construct this source function f from noisy measurements where the white noise here lives in geodesic space. Okay, and one thing we can prove, so let's just look at the simplest case. This is a linear problem, Gaussian noise, so you know you would want to take a Gaussian prior here, and for reasons that I will explain on the next slide, you take a standard Gaussian process prior, your favorite Gaussian process method, so this is modeling a random function in an infinite dimensional space. And here, for some reason, have to do with the geometry, we need to rescale it at the boundary by the inverse square root of the distance function to the boundary. And then you can compute the posterior distribution, which in this linear Gaussian case is pretty simple. We implemented this. And here's a first Bernstein-von Mises theorem, which only holds sort of for nice test functions. So I compute my posterior distribution. F is a draw from the posterior distribution conditional on the data. I pick a nice infinitely differentiable smooth function on my manifold. Then I can look at the random variable that is generated from looking at the distance between my posterior draw to the posterior mean, or the MAP estimate. These are the same in this case. And I integrate this against a nice test function. I scale it by the inverse noise level of my equation. And then this is a random probability distribution, the law of this random variable. And it converges weakly to a normal distribution that has a particular covariance that is formed from basically computing the adjoint of the forward operator, taking this inverse, and then applying the forward operator again to my test function psi. This is the limit if you've ever seen a statistics, like first statistics course on linear models. This is what you would expect from the Gauss-Markov theorem to happen, but of course this is in infinite dimensions. So when I first sort of tried to write some proofs of this, I found out that actually if you want to prove that this inverse exists, even for this simple transport PD example, it's not so obvious that this inverse map can be applied to it. So luckily I had a sort of pure PD colleague that I play football with a lot, and I started talking to him, and he's an expert in microlocal analysis, so he actually proved that this inverse properly exists. So and this is not completely trivial, because even if you, for the Radon transform standard on the disk, apply u star u to the constant function, you would expect something smooth, but you don't. You get something that is not smooth. So the mapping properties of this normal operator, information operator, are somehow subtle. But we could settle it, and at least for smooth aspects, you do really get this Bernstein-von Mises theorem, which tells you that at least if you just want to make inference on such a nice linear functional, you can do it. And one consequence of that is that you can also find the asymptotics of the actual Tikhonov regularizer, or of the MAP estimate. So here in the continuous model, we just solve this optimization problem from sort of squaring out the least squares term and ignoring the bit with y. And if you find the optimizer of this problem, then you can find the exact limit distribution of the Tikhonov regularizer when you take an inner product with a smooth function, which allows you to get a credible set of that form. So if you compute your Tikhonov regularizer, you indeed just use the posterior quantiles to look at the confidence interval for this inner product with psi, and you tune your posterior quantile so that this credible set has posterior credibility 1 minus alpha, then indeed also the frequentist probability of the true inner product with f naught lying in this credible set will converge to the same probability. And moreover, you have exact asymptotics of these quantile constants which go to the optimal thing. So for this problem, the Bayesian method actually does better than any other method, or at least no worse, and you can prove it rigorously in this way. And it is also circumventing having to estimate this nasty limiting asymptotic variance that you might not otherwise be able to estimate. So in a way, for linear inverse problems, this gives full guarantees, at least for such one-dimensional subproblems. So in some sense, of course, now you can ask what happens if psi is not smooth. You can, and can I maybe reconstruct the entire function f globally somehow? And that's what I'm going to talk about. Well, okay, we implemented this. Let me talk about this later. Let's look at a nonlinear problem where this theory is a bit more difficult. Yeah. So you look at something that is a second-order elliptic PDE. You could also, I just took the Laplacian here. You could take some given elliptic second-order operator too, and you add a potential to it. So this is sort of a solution of the time-independent Schroedinger equation, and you ask yourself, maybe I see the solution of this PDE with noise, and I want to infer the value f that somehow describes how this solution depends on the potential. There is a classical probabilistic representation of the solution of these PDEs, which is in terms of a certain functional of Brownian motion, or well, of the paths of Brownian motion, and you see immediately that this is a nonlinear problem in the sense that the map that sends f into UF is not linear in f. So we cannot use formal conjugacy arguments for Gaussian priors like we did in the previous proof. So here you have to really think carefully whether the Bayes method can still be trusted. And if you think of this, what this means physically, if you have no potential, then you just see the standard of the solution of the Laplace equation, sort of the, well, I probably don't have to explain this here, but this potential somehow models a cooling in the steady state temperature distribution in the classical heat equation, where the potential, if it is bigger, it will sort of cool down the temperature here. And the question is, like, from images like this plus white noise, can you infer the potential? And there are some papers where people study these problems in inverse problems. Okay, so we have this additive white noise. I will now, if you want to give some guarantees for the Bayesian method in this problem, you need to regularize a bit more. Gaussian priors seem to put too much mass on sort of nasty things in the parameter space where the inverse problem is not so well posed any longer. So you do something a bit more like in the previous talk, where you expand the log potential in some wavelet basis or in some of your favorite dictionary basis function. You put some uniform coefficients that scale somehow to produce smooth functions on the log level. And the first question you can ask is, does the posterior, if I think that there is a true potential F naught that generated the solution of my PDE, sort of the ground truth has some smoothness, does perhaps the posterior somehow put most of its mass on a small ball around this true potential F naught? Yeah? So this will tell you some consistency result that the posterior actually converges somehow to the true state of nature, but it also quantifies the rate of convergence, and you can prove something like this, namely that the distance of the posterior draw to the true function in L2 scales at this convergence rate, where I remind you that epsilon is a noise level, so scales like 1/squared of sample size in a discrete model, and you get a certain dependence on the smoothness of the potential, which is S here, and on dimension. And you can also prove that this rate is optimal. You cannot improve it, not just for the Bayesian method, but there's an information theoretic lower bound that tells you this rate cannot be improved on. But again, we want to not just get a contraction or a consistency result, because these results don't justify credible sets. You need to say more precise things about the posterior distribution, and that is when you try to prove Bernstein-von Mises theorem. So just like in this first order transport PDE case, I can initially just study inner products of my posterior draw minus the MAP estimate with a test function, and ask whether this converges to a normal somehow. But in order to get some sort of convergence in function space, I will sort of, actually insist that I'm not doing this for a fixed psi, but I'm going to try to reconstruct the norm of an infinite dimensional space by taking a supremum of a many, many functionals, where then the class of psis I will have to pick will somehow be dictated upon me by the complexity of the problem. So we want to prove that this posterior process, simultaneously indexed by the elements of psi in capital Psi, converges to some Gaussian process, where on the right-hand side you will, get something that depends on the covariance that appears in this limit distribution. And you can work out what this covariance is, and in a way, therefore, in terms just of this limiting Gaussian process, you can decide in which function space you will be able to converge to that variable. And this is what this slide tells you, which is a bit more technical, but if you do the PDE analysis in this problem, and if you know a bit of Gaussian analysis, then you can define a Gaussian process whose covariance is given by a Schroedinger operator acting on these test functions and scaling by the solution of the true PDE. So this is the canonical limit distribution that the Gaussian posterior will somehow converge to. And if you're going to converge weakly to it, this limit distribution, this Gaussian measure in function space, will have to be tight. If it is not tight, you cannot converge weakly to it, because the necessary condition of weak convergence is that the limit is itself tight. So I can entirely decide whether or not the Bernstein-von Mises theorem will hold true for weak convergence by checking whether this limit distribution lies in a certain negative order function space. And it turns out that you just prove using some, tools from Gaussian process theory that if you act on sort of alpha times differentiable test functions of compact support within your domain, you need to require that alpha is at least 2 plus d halves for you ever to be able to converge to that limit distribution in this elliptic case. And this plus 2 here has to do with the 2 ill-postedness of the problem. Yeah? So it doesn't come from d halves, it's kind of intuitive, has to do with regularity of white noise, and the plus 2 comes from the inverse problem. But and it is impossible to get the Bernstein-von Mises theorem in this in any stronger topology, which also gives you retrospectively an insight into Friedman's negative results somehow. Why you cannot get it in L2, because you would take a supremum of a too large ball here. Okay, and so then you can indeed prove also simultaneously in psi that this posterior process in a metric for weak convergence converges to this canonical Gaussian limit distribution. And if you compare this, so I will not go through the details of this statement now. It's a bit technical, I don't have the time for it. But sort of if you go back to the philosophical sort of statement, what Castillo and I proved back then, in the direct problem, but there's no inverse problem, you can have the Bernstein-von Mises approximation not in L2, but in this dual space, sort of in a weakly if you want. And if you have an inverse problem, you will typically pay the degree of ill-postedness of the inverse problem, which here in the elliptic case is plus 2, in this sort of dual norm. So you will get a slightly weaker norm in which you can expect the Gaussian approximation to hold true. And so, I don't know, do I have 2 more minutes because we started slightly late?
Well, we started 10 minutes late, so you can...
So I can do a bit. Okay, good. Okay, so we have this sort of very strong approximation. The question is now, can I somehow use this Bernstein-von Mises theorem in this weak space to get a credible set or confident set about the entire function now, and not just about the nice inner product of this function with a test with some psi? Well, okay, so the first consequence is if you do this same game with a test function that is in C alpha, where alpha is larger than 2 plus d halves, you get the same result as before, that for these one-dimensional characteristics, you will actually have a proper confidence set. So you can trust the confidence set, yeah? And the credible set. So now, of course, now you want to do this, and that is maybe sort of if I talk to my colleagues in mathematical statistics, this is sort of the one thing where things become a bit more well, not contentious, but there are some issues how you would interpret that. You know, what Friedman's classical negative result tells you, if you do a regression problem, or if you even do this in this inverse problem setting, you should not compute a credible ball when you take the standard Euclidean distance. Mostly because, you know, there was a bit of something about this in one of the talks earlier today, that in a way balls don't interact so well with these Gaussian limit distributions to which you converge. Yeah? So there's some theoretical evidence that one should not just give same weight to all the frequencies in your series expansion. It's a theoretical finding. What this theorem tells you, what you should do is you should compute somehow an ellipsoid in the support of your posterior, where you take, say, a ball in this dual space. And then you might ask, well, actually, this is a pretty weak norm, so maybe I don't get to see the finer properties of the unknown potential in this case in the Schrödinger equation, or of the conductivity if you do the same game in the sort of divergence form PDE. But actually, because the posterior in itself also reproduces regularity properties of the prior, you can use arguments from interpolation theory that tell you if you actually just basically compute this credible ball in C alpha C star, which means that you intersect all the one-dimensional credible sets from the previous slide across a ball in C alpha C, so you have simultaneous, it's almost like a multiple testing approach for many, many, many psi's. If you do that to construct your multi-scale credible band for F naught, you will get coverage, and using interpolation theory, if you look at a much stronger norm, here L1, on a compact subset of my domain, which is not the norm in which the Bernstein-von Mises theorem holds true, in which it cannot hold true in this space, but you still get the near optimal diameter. So there's a theoretical result, but if I wanted to explain what this means to a practitioner, it means that instead of trying to compute Euclidean balls when you compute credible sets, or typically you draw many posterior samples and then you discard some of them, the outliers, and the decision rule according to which you discard outliers should be one where maybe you take this multi-scale approach where you test sort of the credibility across a large class of linear functionals and intersect what you get information from that, instead of really just doing some sort of naive high-dimensional analysis. And this is something that you can see this, of course, without even considering inverse problems. You can see some of these phenomena in practice. Yeah? I mean, in simulations. Maybe to wrap up. So I should say, these results that we have now give a template to prove things like this also in other inverse problems. But I really would not wish this talk to be understood as saying that Bayesian methods in inverse problems always work. Yeah? So I could also have given you, a talk where I show several pictures where you get highly questionable outcomes, and I don't want to say this, but what I'm saying is that if you carefully choose your prior, there is some theory that actually tells you not only will your Bayesian method work, but will actually be optimal. And in particular in this nonlinear PD example, I actually don't know a frequentist alternative method that does the same. So it is maybe a canonical way to construct good inference rules for inverse problems, but to justify them is somehow a problem-specific game, particularly because whether the Bernstein-von Mises theorem holds true or not has to do with this limiting Gaussian process and this invertibility of the Fisher information that is an assumption in the parametric model. In these infinite dimensional models, you cannot assume or not. It is basically something that you have to prove, and it typically boils down to proving a certain PDE, the solution to a certain PDE exists, which is dictated to you from the forward problem. So for the Schrödinger equation theorem, for instance, you can prove that this information operator is invertible. Already, if you would do the same game for divergence form PDE, where you want to make inference on the conductivity, you get to see very fine properties where you need to know that the gradient of the solution of the forward map doesn't vanish somewhere, and these are things that are not so obvious. So I would not want to say that this always works, but there are situations where we can prove that it works. Another interesting question is that in the previous talk there was always uniform priors, so in a way that the prior was bounded in function space, and something that Andrew has been advertising sometimes is to take a Gaussian prior on your log parameter. And we do have some results now that might indicate that this could be good, but I generally think that Gaussian priors put a lot of mass to sort of nasty parts of the parameter space where the inverse map starts to be pretty unstable. So there's certainly a question mark there that has to be addressed. If you want to read on any of this, so the Schrödinger equation stuff is in this paper, which is on the archive, and the transport PD stuff is in a paper that is to appear in the Annals of Statistics. So thank you for your attention.
Questions for Richard? Okay.
So one question is regarding your first result. So you said it's micro-local, but you say not in the smooth class. So what do you use? You use a holomorphic calculus, or
so here what happens is that if you take an infinitely differentiable function, a priori it's not clear that U star U inverse can be applied to it. Now, what you have to do is you need to somehow say that, well, so you have to prove that the inverse of the information operator can be applied to it. Now, you can try to study U star U as a pseudo-differential operator and check whether the classical Boutet de Monvel calculus applies to it, but it doesn't. It doesn't.
Holomorphic, so it's holomorphic calculus. Yeah.
Well, you need some more refined results that model this boundary behavior. So there are some lecture notes by Hermanda in the 70s in Princeton where he worked on sort of cases where this transmission condition that you usually check for pseudo-differential operators is not satisfied, but if you put some extra weight of -1/2 in the sort of pseudo-differential operator symbol, you can still invert it. And Gabriel Patanine, who's an expert in microlocal analysis, is our head of department here, was, he succeeded in proving rigorously the invertibility, but it's not obvious that it exists a priori.
Okay, but the result is then in a weighted C-infinity class. So
yes, so you can prove that U star U gives you an isomorphism of C-infinity functions weighted with the 1/square distance to the boundary to C-infinity, and then you can also go back.
Okay, thank you.
It's in the paper, it's all written in detail.
So the issue is the weight, not the smoothness. So
it's not, well, I mean, of course, at the boundary, the smoothness has to do with the weight, so it has, in a way, has to do with it.
I have another question. So your second results, they are in the CS in some Hölder classes dual.
Yeah.
So will they also hold in suitable Bezoff classes?
Yeah, I mean, so you see, it all has to do with this Gaussian process, which is the image of white noise under a Schroedinger operator, and you need to determine in which spaces this guy is a tight Gaussian probability measure, and you can do that in Bezoff spaces too, and you will generally compare to the standard result for white noise in a Bezoff space lose smoothness too.
Yeah, but I'm asking because the Bezoff classes are more accessible to parametrization by wavelets and other
well, but if you think C alpha is B alpha infinity infinity.
Yeah, but the infinity is not so, but you could do it with a finite index.
Well, this is a good question. Mathematically, at the moment, I don't know how to do this because this proof actually, I have to say, is not completely trivial. So it's like a 40-page arguments that one has to do. So, but in the direct case, if you don't have the inverse problem, then my answer is yes. But for
the finite fine indices, I'm asking because then you have a chance to build bases and leverage computation. Yeah, this one.
I mean, I have not addressed computation in this talk at all, and but I think wavelet basis. I proved the result for prior that is expanded in a wavelet basis, very much like what you have been talking about in your talk and doing.
With these bases, there are separability issues. Yeah.
But yeah, I mean, so you see, you have to make a compromise. There's still a certain gap between theory and practice.
All right, let's thank Richard again.